Greeting, guys. This is Mr. Glenn, ACT Prep Chicago. Um, we're doing part two of the science. I think we did from 1 to 23. Now we do from 24 to 40. This is the answer explanations for the online ACT practice test one. So the way you get through this is you go to act.org. Um, if you click on, you would have to click on the ACT test. Let's just say if we started from the regular screen, right? So if you were starting the regular screen, you would start there. Let's click this out. You would say start your journey, and we go to take the ACT. I think that's how you get yes. And then you would go to what? Test prep, and then you would go to free practice tests, okay? And then the practice test PDF form is here. These are the PDFs. I'm going to open it because I use the answer key sometimes. Um, but we're going to do the online practice test. So I'm going to have this open, this tab open. I'm going to open another tab, the same thing. Um, so I already have it set up on my online practice test, but I didn't go. There we go. All right, but I'm going to go back to the original so you can see how I get to it. So again, you would start there, you student, no, not student parents. You would hit start your journey, take the ACT, test prep, free practice test. Um, this is the online practice test is what we want. So start practicing now. Then we go to this with online practice test. And if you scroll down, you'll see here the full length practice test. Let me zoom right down. Yeah, see more. I'm zoomed in because my eyesight ain't the greatest, but I'm going to see more of what they have to offer. I guess it's not even necessary at this time. Maybe I can zoom back in a bit. So it's bigger print, easier for me to read. And we're doing the science, and we're going to do not timed, and we're going to do practice test one, which is right here. Okay, digital version. I'm going to open up the PDF. So it's loading up the digital version. I'm going to open up the PDF too. The reason I do that is because these, again, like I showed you before, just so you can see, these are the same PDF and online digital version. When you guys take the test, you'll be taking an online version. So that's why I'm doing digital because it's more similar to what you will be doing when you take the actual ACT. But yeah. But I want to load up this one. And I just want to show you too. So just to see which question we are on now, to be real random. So we finished part one of the science, we finished up to 23. 23 was the last one. So we're on 24 now, which is passage five. And if we look at passage five, the first question says a linear region of a graph, right? I'm gonna zoom that in a little bit. Anyway, linear region of a graph. A linear region of a graph is a range of data that can be approximated with a straight line based on figure one. For alloy Q initially at temperature 550 degrees, which the following ranges of F best represents the linear region. If we go to question 24 on here, so I'm going next. You see it, the question numbers are here, 13. Should be the same exact question. Is that the same question? Right. Yeah, that's the same question. Initially temperature, this question, and that one. Okay, yeah. So same as that. But if I load the PDF too, I'm able to see the answer key. So if I have to check an answer for whatever reason, like we're not 100% sure, I can go back here and I can check these answers. Okay. All right, without further ado, let's begin. So a linear region of a graph is a range of data. Linear means straight line that can be approximated with a straight line. Again, with science too, you go straight to questions. We don't read any of this because you'll see that a lot of these questions can be answered without fully understanding what this experiment is about. Trying to get a full understanding of the experiment will waste your time. You don't want to do that. A linear region of a graph is a range of data that can be approximated with a straight line. Based on figure one, where's figure one? Figure one is here. For alloy Q, that must be the only alloy in there because the only thing different in figure one is different temperatures and they measure in length based on whatever the F is. I don't know what F is, but I don't need to know. For now, based on figure one, for alloy Q initially at a temperature of 550 degrees, this is the dotted line. You see what I'm doing? Two pieces. I go to a piece and I go look for it. Back and forth, question, figure, question, figure. Which of the following ranges of F best represents a linear region? Or it would be what? With a straight line, linear straight line, right? So where could we have a straight line for 550 degrees, the dotted line? So this between 0 and 10? No. Between 0 and 10, you do what? Curve, right? Between 10 and 20, it goes up and then comes down, but this part is pretty straight here. I'm looking at the answer choice between 20 and 30, because they are 20 times 10 to the seventh is just 20, because all of them are times 10 to the seventh if you look at the units. So between 20 and 30, no, definitely at 20 and 30, that's parabola more. That's a U, you follow? And what about between 30 and 40? 30 and 40 is actually the correct answer. That's the straightest line for any of the ranges that we were provided. That region between 30 and 40, that's about close to straight line as you can get, given the answers that we were given. So that's that. All right. Consider the two trends shown for alloy Q, initially at the temperatures of 280 degrees and 550 degrees. So two trends shown for alloy Q. Okay, from F40 times 10 to the second degree, F48. These lines were to continue along the same trend at which the following values of F with the average crystal length most likely be the same. Okay, so we're talking about this one. So the L must be the average crystal length. I figured we're talking about this one because they said two temperatures, 280 and 550. They said these trends. So if these trends continue from 40 here to 48, that stops about there. That's where they stopped. Yeah, they both stopped about 48. If these lines were to continue along the same trend, means, okay, so if they continue along the same trend, we can see that the dashed line should what? It should continue to go up. Get my pencil out. It should continue to go what? Up. See, it wasn't working. Yeah, not working. I know I used it for another computer, but does that make a difference? Oh, shoot, I'm not even recording. I forgot to hit record. Or did I? Is it right? I'm recording? Yeah, I am recording. Okay. Something is wrong with my pen. That's going to be a problem. Let me see if I can finish this one without the pen. See if I can finish it. Okay, so if we continue the trend, this was going to trend like this, and then this sideline is going to continue like this, right? So these lines will continue along the same trend at which of the following values of F, with the average crystal length most likely to be the same. When are they going to meet? So if we continue the trend as much as possible, And then that line, my pen would be great to have right now. So it looks like 60 is where they meet because it looks like this is 40 to here, 40 to here. And if we increment that another about the same unit, that's about there. So 60 would be about right there, right? If we continue the same line of thinking or the trend value. So right, and that's about where they meet. So I'd say 60. 70 would be over here. They would be way past where they met. So I would say 60. So it's about continuing the trends that you already see there. So it'd be 60. Very good. Okay, based on figure one, let's put this over. Okay, based on figure one, what's the following combination of values for initial temperature and F would produce the shortest average crystal length and an egg ingot of alloy Q? Smallest L would be produce a temperature of. Okay, so based on figure one, just find combination values for initial temperature and F. Figure one, initial temperature, 280 or 550, and F would produce the shortest average crystal length. The smallest L was L, so the lowest L is here, would be what? Well, 550 degrees have lower L's, so you want 550 degrees. And would you want to be at 10 or 40? So 10 is here, 40 is here. Ooh. Okay, so 10 is there. And 40 is a little bit lower, not much. But so yeah, it would be 40. Gotta really watch that last one. So that's going to be the shortest combination. All right, the following table lists the mass of silicon in 50-gram samples of 4 different alloys, one of which is alloy Q. Given the composition of alloy Q, which sample is most likely alloy Q? Okay. So what are we doing? Mass of SiG. Following table is the mass of silicon in 50-gram samples. So how much silicon is in the 4 So how much silicon would be in alloy Q would be the question, right? Silicon here, let's say my mass alloy Q is 10.8. Oh, you got to do a lot of math on that. Okay. So 10% silicon. So if this is mass of G, so the following table is the mass of silicon in 50-gram samples, right? So they said it's 10% silicone and alloy Q. So if this is 50-gram samples, right, we need 10% of the 50-gram sample should be silicone and alloy Q. So if we did 10% of what? So if we did 10%, man, I wish my people, 10% of what? Of 5, of 50, sorry. 10% of 50 is equal to what? And you can't use a calculator on this portion of the test. She was working. The weird thing is the other one, I didn't have to do anything to sync it. I wonder if it's something with the screen. 10% of 50, right? So then you do what? 10%. So to do 10% of any number, you do what? You move the decimal one place to the left, right? So if we have 50, you have to bear with me because I'm using my mouse and my pen is not working for whatever reason. I figured that out, that computer stuff. So if we go one to the left, right? That's 5. So 10% of 50 would equal, so that means the decimal would be here 5.0, which would be 5, right? 5.0 is 5. And so essentially we're looking for which sample has close to 5 grams, and it would be sample Z. So then that means that sample Z is probably alloy Q because it has 5 grams of silicone, which is 10% of the 50 grams, which matches the 10% silicone that's in alloy Q. A lot of work for that one. Not terribly hard. So that one was D. Okay. Sample Z. I know that's good. I'll check it though. Which one was we on? Which one were we on? Let's go back. This was, I was item 27. Yeah, 27 is D. I figured as much. 28. Based on table one, if an ingot of alloy Q had a mass of 200 grams, that ingot will contain what mass of Mg? This is going to make us do the same thing again. So Mg is magnesium, which is about what? 22%. So no, this is percent by mass. So it's 0.22%. It's not 22% because this is 88.7%. This is 10%. This is 0.22%. So this is less than 1%. So that's really low. So if we think about it from that perspective again, we have what? We have 200 grams. We have 200 grams. And we need to do what? If an ingot of alloy Q had a mass of 200 grams, um, so just so you say, so let's say we want to do 1% of that. Should do that. Let's do that. So we want to do 1% of what? Of 200 grams. Okay, 1% of 200 grams. So 1% of anything is when you move the decimal place 2 places to the left. So 10% you move it 1 place to the left. 1% you move it 1 place, 2 places to the left. So that's going to be 2. So it's got to be less than 2 if it's less than 1%. Now let's do 0.1%. So we can do even more. We'll do 0.1%, which is what? That's 0.1%. So obviously that's going to be moving it what? 3 places to the left. So 0.1% of what? Of 200. It's going to be moving it 3 places to the left. So again, up here, when we did what? When we did 1% of 200, that's equal to 2. Because when you move it, the decimal place is not written, it's understood to be to the right. We move it 2 places to the left. That's going to be equal to what? 2.0, which is 2. So 1% of 200 is 2, 2.0. So that means 0.1%, we got to move it 3 places. So it's not written, it's understood to be here. We go 1, 2, 3. And you can't use a calculator for the science portion of the exam. So this, all you got to do all this by hand. So 0.1% of 200 is going to be 0.2. Follow? 0.2. So that's 0.1%. We want 0.22%. So if we double that 0.22, so 0.1% of 200, then we can do what? We could say that if 0.1% is 200, then if we double 0.1%, that means that what? 0.2% is what? Of 200 would be 0.4. Do you guys see that? Put it down here. Because we just double. So if we double the percent, we double the outcome, right? So if it's 0.1% of 200 is 0.2, 0.2%, that's double 0.1% of 200. We just double 0.2 to get 0.4. So if we want 0.22, it's going to be closer to what? 0.44, which is answer choice B. I hope you guys get that. All right, based on the results of studies, from which of the 5 leachates was the greatest percent of DOC absorbed by CM? Okay, so we're on a different passage now. Okay. So based on the results of the studies, so we got study 1, study 2, study 3. From which of the 5 leachates was the greatest percent of DOC absorbed by CM1, CM2, and CM3? So CM1, the greatest percent Leachate DLC absorbed by CM1 was pine. You see that? So CM1 there, that's pine, because that's about almost 45%. So we know that CM1 was going to be pine, so it's either C or D. If we wanted our tool on to our tool for our answer eliminator. You know what? Let me see if I can zoom out on it too. Oops, that's not what okay. Technology ain't working as seamlessly as I like, but such as life sometimes. Okay. That's a little small, go up to 9%. Just want to get a little bit more of the picture. Okay, so we know if we do our answer eliminator tool, we know that what this is gone and this is gone because pine should be CM1. That's the highest absorption. CM2, which was going to be study 2, the highest one is magnolia. So both of them are still in play. And then CM3, we have magnolia again. So magnolia twice. So that means that's gone. So that means the correct answer for that one is D. Okay, answer eliminator is kind of cool. I don't necessarily need it, but it helps. I guess as we going over these, you can watch. Okay, based on the results of study 3, the percent of Leachate DLC absorbed by CM3 averaged across the 5 types of leaves is close to which of the following? CM3 is here, the average. Average is a measure of central tendency. So we had here, which is about, so in the middle. So I can almost draw an average line if you look at this, right? Whoops, I didn't mean to got my pencil up there. Okay, that's all right, I use it up there. So average line, I can almost draw an average line in the middle, right? So if I draw a line almost in the middle, because average is a measure of central tendency, I'm going to guess. Now you could do it mathematically if you want. You would have to do it based on estimates, right? But if I draw a line kind of that represents the middle of all of these, I'm drawing it close to 40%. Um, so it has to be D, right? If I do this line lower to 30%, that would not represent the middle really. That would represent the lower ones more, but it won't represent the higher ones kind of shifting that average up. And obviously 10 and 20 would not represent the average because those are what is it doing that? Yeah, I just want to move it. There we go. So if you got 20, that's low. That's not an average, because average got to be somewhere in the middle of these. Average is a measure of central tendency. So I can look at that and tell you that the answer is going to be D, because that's probably the closest to a middle value. Okay. Um, is a statement CM2 absorb? Now, if you want to do that last one mathematically, right, you would have to get all of these CM3, add them up, divide by 5. So you could do it that way, but that's just a lot of work, right? So this line is about, if you average, it's about 35, right? This is about 50. I won't say it's a lot of work, but it's more unnecessary. If we average this one, this is close to, I would just say this, I would just put it 30. It's not 30, it's about 32. But because we don't have a what calculator, we're just gonna put close to, this is close to 55, because you can't use a calculator in science. Do you look up here, you can see in the science tools, you don't have a calculator. Okay. So that's why you know you can't use a calculator. That's how you know you can't use a calculator. And then this one's going to be close to 35 again, right? You can kind of see what numbers in the middle. So if we want to do it mathematically, we can add them all up. So 35 plus 35 is 70. And I would do 50 plus 55, that's 105. So 70 plus 105 is 175 plus 30 is 205. And you divide that by 5. If you divide 200 by 5, you're at about 40. So actually a little bit over 40. You guys see how I did that? So I did 35 plus 50 plus 30 plus I got 205. If you add all those up, you get 205, right? I do it another way just to make sure I got it right. So this is 50, 30, that's 80, that's 90, plus 30 is 120, plus 50 is 170, plus 35 is 205. And if you do 205 divided by 5, well, let's just do, because we don't have a calculator, we're going to do 200 divided by 5 to ballpark it. Well, we know that 200 divided by 5, because remember, averages, you add all these up and you divide by the number you have. And that's going to be close to what? 200 divided by 5 is 40. So that's going to be close to 40%. That's the way you could do it if you want to do it mathematically. But like I told you the first time, if you look at it, average is a measure of central tendency. You just look for what's in the middle. So I would have gotten that right and saved myself a lot of time. There's a statement, CM2 absorbed a greater percent of DOC in the maple leachate than CM3, supported by results of studies 2 and 3. So we're looking at the maple for CM2 and CM3. CM2 maple here was about a little less than 10%. CM3 maple is way more. It's about 35%. So what's the statement? CM2 absorbed a greater percent? No, it did not. CM2 did not absorb a greater percent. CM2 absorbed 7%, whereas CM3 absorbed 35%. That's right. Based on the results of studies, which of the three clay minerals, if any, reduced the DOC in the oak leachate by more than 50%? So I'm imagining if the percent of leachate DOC absorbed by CM1, that would mean that it would what? It would reduce the leachate DOC is absorbed by CM1. So if it's more than 50% for the oak, you look for which one is more than 50. So CM1 is not. CM2 is not. Because it says, if any, reduce the DOC in the oak leachate by more than 50%. If you look at the y-axis, it says percent of leachate DOC absorbed. So the DOC absorbed. So wait. No, percent of leachate DOC absorbed by. So DOC is absorbed by this. So that means that the DOC is being taken from it. So that would mean it would be reducing the DOC in each of these different leachates. Right. So that's what this chart is pretty much showing. So, and then CM3 got up to 50%, but it says more than 50%. So it'd be none of them because none of them had 50% for the oak, bigger than 50% for the oak. Is a mixture of any of the leachates and any one of the clay minerals properly considered a solution? This will require probably background information. Because what makes something a solution? And the answer choices can help you, but not the yes, yes, no, no, the reasons. Because the clay mineral particles are dissolved in the leachate. Is that right? Are the clay mineral particles dissolved in the leachate? The clay mineral particles are not dissolved in the leachate. The clay mineral particles are dissolved in the leachate. The clay mineral particles are not dissolved in the leachate. So we have to know, are the clay mineral particles dissolved in the leachate or not? 3 studies done examined DOC absorption by 3 clay minerals. What is DOC? DOC, dissolved organic carbon. It's subsequently removed from the water if it is absorbed by clay mineral particles. 3 studies are done at a lake examine DOC absorption. So these clay mineral particles. Bleach was mixed with. Oh, here it is. The mixture was stirred continuously for 2 hours, then filtered to remove all solid particles. The resulting liquid, the filtrate, was analyzed for DOC, the percent of the leachate DOC that had been absorbed by CM1. So they mixed 10 grams. So the 100 volume of the leachate was mixed with 10 grams of CM1. Was it dissolved in it though? That I don't know. Is a mixture of any one of the leaches and any one of the clay minerals properly considered a solution? The leachates, mixture of any one of the clay mineral. So if I mix the leachate and the clay mineral, would it be considered a solution? I guess you would say it dissolved because if it if it absorbs some of the if the leachate absorbed the clay minerals, then it would have dissolved in it. So yes, because the clay mineral particles are dissolved in leachate is what I would say, right? Because it says the clay mineral particles are dissolved. Wait, are they dissolved in the leachate? No, the clay mineral particles, they dissolve. No, this says a 100 milliliter of leachate was mixed with 10 grams. The mixture was stirred and then filtered. And then the CM1, the percent of leachate DLC that had been absorbed by CM1. That's a tricky one. It's a mixture of any one of the leachates and any one of the clay minerals properly considered a solution because the clay mineral particles are dissolved in the leachate. I think they are dissolved in the leachate because when you stir the leachate in the clay minerals, the clay mineral ends up absorbing some of the leachate. Which would mean that the leachate is actually dissolved in the clay mineral particles. I would say actually no, because the clay mineral, the leachate is dissolved in the clay mineral particles. Clay mineral particles absorbs the leachate, so those clay mineral particles are not dissolved in the leachate. So I'll actually say D, but I don't know this one. It requires outside information. You got to remember that. Let's look at the answer choice though. For that one, which one is that? 33. It's D. Okay, I was right. And I think I'm right because when you look at the experiment, it's the clay mineral particles that are absorbing or dissolving the leachate. It's not the leachate dissolve the clay mineral particles. So the clay mineral particles are not dissolved in leachate. It's the other way around. The leachate is dissolved in the clay mineral particles. So that's what I would say on that. And I was right. Okay. I think that's right. I'm not a science person by background, I'm a math person by background, but you don't have to be a science person necessarily to get these. It's consuming, all right. What if I'm wrong? In terms of the explanation, I got the right answer. Okay, in lake water, DLC is broken down into simpler compounds by electromagnetic energy in the visible wavelength range. What action was taken in the studies to prevent this process from occurring? Let's read that. In lake water, DLC is broken down into simpler compounds by electromagnetic energy in the visible wavelength. What action was taken? Oh, they filter them. Each mixture of these and filter lake water is placed. No, each mixture of filtrate and clay mineral was placed in the dark. Each mixture of leaves, where they were filtered. Each mixture of leaves and lake water was filtered. Each mixture of leachate and clay. What was filtered? I think it was the leaves and lake water. Because if DLC is broken down by simpler compounds, we don't want those compounds in there breaking down the DLC. We only want the clay mineral to break down the DLC. So what action was taken in studies to prevent the DLC being broken down by other compounds? That means that we would have to get the compounds out of the lake water, which means that the mixture of leaves and lake water would need to be filtered. It had to be C. I think I remember reading that too. The following procedure was performed for each type of leaf. A 100-gram sample of leaves was mixed with 1 liter volume of filtered lake water. The mixture was then placed in the dark while leaching occurred. At 10 weeks, the mixture was filtered to remove all solid particles. Yeah, see that the mixture of the resulting liquid was analyzed for DLC. Wait, or it could have been the mixture was placed in the dark for 10 weeks. mixture of leaves and filtered lake water was placed in the dark. Each mixture of filtrate and clay mineral was placed in the dark. It wasn't filtered in clay minerals, is that so we know it's not this one that wasn't placed in the dark. And we know it wasn't the clay minerals and leach that was filtered. It was the lake water and the leaves that were filtered. So both of these things happened. It was placed in the dark and the leaves were filtered. DLC is broken down to simpler compounds. Oh, DLC is broken down into simpler compounds, not by simpler compounds. So DLC is broken down into simpler compounds by electromagnetic energy in the visible wavelength range. So the electromagnetic energy is what breaks down the DLC. And if we don't want that process happening, it would not be filtering it. It would be put in the dark. Because if you put in the dark, then you don't have it exposed to the electromagnetic energy, which I think sun. Yeah, well, anyway, that's I think that's why they put in the dark. At 10 weeks, the mixture was filtered to remove all solid particles. You almost got to understand this experiment. So I think that's right, though, because it says visible wavelength range, electromagnetic. So in the visible wavelength range, if you put in the dark, that you don't have any visible wavelength, right? That's why you put in the dark. So that way the DLC is not broken down into simple compounds. Yeah, it's the dark. I believe in that. Let's check that one out. 34. Yeah, 34 is F or A, but A and F are the same. All right, hopefully you got that. Consider the current shown on the ammeter in figure 1. Based on the results of experiment 2, when the current was measured, what was the relative intensity of the light? So this is the current shown on figure 1. All right, this is the current. Based on the results of experiment 2, where's experiment 2? Here's experiment 2. When this current was measured, current, what was the relevant intensity of light? That must be, is K the relative? Table 2 shows the current, and K, what's K? And K were measured as the intensity of light was varied. We gotta look at what's K. K is the difference. K is the difference between E and M. Oh boy, okay, this is gonna be a tough one. So with these, you don't get stuck. Let's see. Consider the current shown on amine in figure 1. Based on the results of experiment 2, when this current was measured, so when you measured the current for experiment 1, what was the relative intensity of light? Was it 12.5%, 25%, 50%, 100%? Experiment 2, with the same set of experiment 1, except without a filter, the current and K were measured at the intensity of, were measured as the intensity of light was varied. Table 2 shows the current and K for 4 different relative. Oh, here's the relative intensities here. Duh. What? So you got to use your answer choices. I should use my answer choice. Okay. So that's that. So what are we trying to connect? Consider the current shown in the ammeter figure 1. When this current was measured, what was the relative intensity of light? When this current was measured. So what was the current for the figure in 1? In figure 1, what was the current? Oh, 19.8 MA. Because I think ammeter measures current, right? Um, Students conduct two experiments that amount of difference in light and striking metal plate. The setup induced light source and a current. A current with an ammeter to measure current, right? So the current was 19.8. See it there. Oh man, you gotta watch the details. So where's 19.8 here? That means the intensity of light would be 50. Jesus. You gotta really be paying attention to details. It wasn't even a hard question, you just gotta watch the details. What aspect of the experimental setup was held constant in experiment two, but not experiment one? That means changed. It wasn't light, because I remember they said in experiment two, they varied the light. It says with the same setup, except without a filter, the current and K were measured as the intensity of light was varied. Oh, no, that's not the color of light, that's the intensity of light. That's different. Or four different relative light intensities. Intensities could be color, I think that is. So the light source, well, that's what the experiment was held constant in two, but not one. Type of metal plate. What did they change in experiment one? The filter was placed between the metal plate and the light source, and the K of the ejected electrons was measured. Procedure was repeated. Oh, it was K, because K, if you look at K, K changed, but in here, K was stayed the same. But was it held constant? They said it measured it, so I don't know if you can say it was held constant. Because they said and K were measured as the intensity of light was varied. Can you measure a constant? So they used the same type of metal plate because experiment two just said they did the same setup as experiment one, except without a filter, the current. With the same setup as experiment one, except without a filter. The current and K were measured as the intensity of light was varied. Table two shows the current. Different, which is, yeah, the only thing so the same setup, so type of plate was the same, light source was the same, color of light varied, with the light intensities varied, I think. Let's look here. Filter was placed between the metal and light source and the cable electron. I mean, to the color of light transmitted, the table one lists the following. The color of light transmitted by the filter, which is what was held constant in experiment two, but not in experiment one. Well, we know the color of light was not constant in experiment one. Was it constant in experiment two? Oh, yes, because it says without a filter. So the color of light transmitted by the filter changed the light. So yes, so in experiment one, because experiment two, because we don't have the filter to change the light, um, the the color in experiment two was held constant. We didn't change it. But in experiment one, we had different colors. Even though K is different in these and K is the same here, because constant is the same, K was measured. So the distance between metal plate and electrode, which is K, I think that is K because it's here, right? The maximum kinetic energy of K is the difference between E and M. Um, Ejected if the energy of a photon striking the metal plate is greater than oh no, that's energy. That's not even distance. Never mind. But it's color of light. You can see. Um, I don't even see distance, but I know it's color of light. I'll explain it to you. Let me just check that one. That was 36. Boy, these take some time too. 36. Yeah, that was F2. Yeah. That's what I picked. I picked F, yeah. All right. Based on figure one, are the particles ejected from the metal plate moving toward the electrode or away from the electrode? And are those particles positively charged or negatively charged? Based on figure one. Where's figure one? Okay. Are the particles ejected from the metal plate? Where's the metal plate? Here. The particles ejected from the metal plate. It says it looks like those are electrons moving toward the electrode. Those are electrons. Are the particles ejected from the metal plate moving toward the electrode or away from the electrode? They're moving toward it. That's the arrows. They're ejected from the metal plate moving toward the electrode. And electrons are negatively charged. You just have to know background. Electrons are negatively charged. Protons are positively charged. Neutrons have no charge. You do have to know that background information. 38, based on the equation in the passage and the results of experiment one, what was the value of M for the metal plate used in the setup? So, okay, based on the equation in the passage, this equation, K equals E minus M, and the results of experiment one, what was the value of M for the metal plate used in the setup? Value of M for the metal plate used in the setup. So we need to know K and E. K is the difference between E and M as shown. So if you add, what do we want? What was the value of M? So you do add M, subtract. So E minus K will equal M if we change that step. So what is E and K for experiment one? Based on the equation in the passage and the result of experiment one. E and K, experiment one, where's E and K? The filter is placed between the metal plate and the light source, and the K of the jet electrons, and they measured the K. How do we know which one they're talking about? So you just repeat it each four additional filters. Each filter, I don't know if I can see. Okay, students have two spins within the vector light and check the metal plate. The setup included a light source, a removal filter, a circuit with animated measured current, a power supply that can be adjusted to measure K in the vacuum tube containing metal plate and electrode. And then the answer is 2.14, 2.20, 2.31, or 2.42. I think we got to know that the relative intensity of light was 50, which means the K is 0.9. And the K was 0.9. I don't know what the E was. Well, K was 0.9 and E had to be 3.10. 3.10 minus 3.10 minus 2.9 minus 0.9. Would be 2.20. Yeah, 2.20. That would probably be my guess. I don't even know if I'm right, but if I was on the test, I wouldn't have time to get stuck on this. That I do know. Based on the equation in the passage and the results of experiment one, what was the value of M for the metal plate using the setup? Right, M and the metal plate using the setup. Yeah, that's what I would guess. So the equation, the passage, and the results of experiment one. So how did I do that again? Why did I subtract? Oh, because based on the equation, the passage, and the results of experiment, what was the value of M for the metal plate? So this was your setup here, right? I think students consider two experiments to examine how the difference in light strength and metal plate. The setup included a light source, a removable filter, a circuit with an animated and measured current, a power supply that could be adjusted to measure K, and a vacuum. And it measured the current here of this setup to be 19.8. The filter is placed between the metal plate and the light source. This is your filter between the metal plate and the light source. And the K of the ejected electrons is measured. This procedure is repeated with each of four additional filters. Wait, this procedure was repeated with each of four additional filters. Each filter transmitted light of only one frequency. Table one lists the following: color of light transmitted by the filter frequency. But how do we know was the first one red? So it'd be 4.4 minus 1 point. No, K is not available, not applicable, not available. No electrons were ejected. So I'm assuming in the setup, because the amp was 19.8, that means that relative intensity and the current 19.8. You had a K at 0.9. I don't know if I'm right on that one. This is a hard one. Boy, this is a tough one. Might be missing something that's pretty easy. Okay, so I would probably guess that one I would come. Let's see if we can come back to it. We'll flag it. Let's see if we can move to the next one and then come back to it. 39. The cutoff frequency for a particular metal is the lowest frequency of light at which electrons are ejected from the metal. Based on the results of experiment one, the cutoff frequency of the metal plate was the cutoff frequency for a particular metal plate is the lowest frequency of light, its frequency of light, at which electrons are ejected from the metal. Lowest frequency of light. So it's not 4.4 or 5.2 because it says no electrons were ejected. That's what the Na stands for. No electrons were ejected. So then, based on the results of experiment one, the cutoff frequency for the metal plate was, it had to be like about 5.6, between 5.2 and 5.6, because it wasn't available at 5.2, but in the 5.6, you had a 0.11, which means that electrons were ejected. Because that's what I think that's what K is. K measuring electrons ejected. Yeah, the maximum kinetic energy of the ejected electron, K. Right. So the energy of the ejected electron, K. And they didn't have any ejected electrons. So the particular metal is the lowest frequency of light at which electrons are ejected from the metal. So that's the K. So Na, and then 5.6 is the first reading we have, but it's a little bit over 0.1. So it may be like 0.01. It could be something smaller than that. So it would be between 5.2, 5.6. Somewhere would be the lowest frequency. Because this is not zero. If this was zero, the lowest frequency would be 5.6. But because this is a little bit above zero, there could be a frequency lower than 5.6 where K is still applicable, even though it's very small. Hope you get that. And then the last one, the relationship between E and the frequency of light is given by the equation E equals HF. Boy, they saved the hard one for the end. This is not easy. Where H is Planck's constant and F is the frequency of light. Based on the data for the green light in table 1, which of the following expressions could be used to determine the value of H? So the relation between E and the frequency of light is given by the equation E equals HF, where H is Planck's constant and F is the frequency of light. Based on the data for green light in table 1, which of the following expressions could be used to determine the value of H? So table 1, green light has an E of 2.31. Oh, that's not so bad. That's just using math. Dang, I keep going to my pen, but it doesn't work. It has an E of 2.31. Right? And we don't know H. And F is the frequency of light. Of green light is 5.6. And this is 5.6 times what? And if you look at the frequency of light, it's 5.6 times 10 to the 14. If you look at the tape, that's what it shows for all of these lights, times 10 to the 14. So your mathematical mind just says, well, how do we get H by itself? Well, because it's what? H is being multiplied times that, right? You could put a what? You put a vertical line through the equal sign. And since H is being multiplied at that, you could divide both sides by the 5.6 times 10 to that. That would get H by itself. So if you divide that by 5.6 times 10 to the 14, right? Cancels on the right side. Okay, and now you got H by itself, but whatever you do to the left side, you have to do the right side. So the answer is going to be what? 2.31 divided by 5.6 1 times 10 to the what? To the 14. Okay. Which is going to be which choice? That's going to be D. All right, let's see now if we can go back to the flag one. Let's see if we can get it one more time. Might just give it up and say we got you got plenty that you can go off of. Sometimes there'll be questions like this. It might take time to get to it, but it may not be worth the video. Okay, based on the equation, the passage and results of experiment one, what was the value of M for the metal plate used in the setup? Oh, you know what? Let me check my answer for that one. 38. Oh, I was right. 38 is G. So I wonder if my thinking was right on that. Because my thinking was this here's the setup, right? This is the setup, but it had a current of 19.8. Um, right? It had a current of 19.8, which means that, and it says when it's a 19.8 current, now it had a relative intensity of 50% too. So I don't know if that alters it, but it had a K of 0.9. When I looked at experiment one for a K of 0.9, that means electric energy 0.9. And I know that what they say was the value of M. And then M was given by the equation here, K equals E minus M. So an electron will be ejected if the energy of a photon striking the plate is greater than the minimum energy required for the electron to be removed from the plate. Oh, I got you. So if the energy is striking the plate is greater than the energy M required for the electron to be removed from the plate. Maximum kinetic energy of the ejected electron K is the difference between E and M as shown in the equation. So maximum kinetic energy of the ejected. So whatever energy that photon particle of light striking the plate. So this is E is this energy of the light striking the plate, and this is the maximum energy. No, this is the minimum energy required for the electron to be removed from the plate because you need energy to remove electrons. So if this is E is greater than M, then an electron will be ejected, and K will be the kinetic energy of that ejected electron. How differences in light striking metal affect K. The setup included a light source, a removable filter, a circuit with an ammeter to measure current, a power supply that can be adjusted to measure K in a vacuum. Okay, and then this is just setup. A filter is placed between the metal plate and the light source, and the K of the ejected electrons was measured. This procedure was repeated with each of 4 additional filters. So this is one. Wait. Each filter transmitted light of only one frequency. The table lists the following. Color of light transmitted by the filter, frequency of light in hertz, E in electron, K in electron volts. With the same set of experiment one, except without a filter. So based on the equation and past one, the results of experiment one, what was the value of M for the metal plate used in the setup? Oh, okay. So it's basically asking us what is all of them. When you subtract them all, you get 2.2. Oh, because this is going to be a constant. M is going to be a constant because the metal plate is the energy required. M is the what? The minimum energy required for an electron to be removed from the plate. That doesn't change because you're using the same metal plate, right? So K, if you do E minus K, you see all of these for E minus K is equal to 2.2. So 2.31 minus 11 is 2.2. 2.64 minus that is also 2.2. And 3.1 minus 0.9 is 2.2. Because that makes sense. Because what? Because the energy from the plate doesn't change. That's what M is. The only thing that changes is the energy of the light intensity that hits the plate, and thus, so as long as E is bigger than M, right? And you see all of these E's are bigger than M, 2.3 is bigger than M 2.2, E 2.6, and you subtract it to get K, right? Because they said, if you look at the equation above, I got it. It takes time. If you look at the equation above, it says K is equal to E minus M. Where what? Where, and then I had to read what K was. So if I do, and you can manipulate the equation too. So K is equal to E minus M. Let me see. Put it over here. I could have manipulated the equation too. So if I say K is equal to E minus what? Minus M, right? If I say K is equal to E minus M, then what? K is equal to E minus M. If I say K is equal to E minus M, so for instance, so we don't, let's say we didn't know these are all the M's, I figured that out, but let's say we only knew the E and the K for this one. So let's just take the first one. Oh no, I was saying manipulate this equation to get E is what to get M. So if we manipulate this equation to get M, what we do is we solve it for M. So to solve this equation for M, uh, the easy way is to add M to both sides, even though we're trying to solve for M, because that way once it's negative, then you have to do some more work. Well, we could do it that way. Let's do it the one that makes sense. So if we're trying to solve for M, we got to get M by itself. So we're going to subtract E from both sides, right? So if we subtract E from both sides, okay, so we're trying to get M by itself. So what we have left on the left side is we have K minus E. Okay. And on the right side, we have negative M. But we still don't have what? We don't have M by itself. So we have to do what? We have to divide by -1 to get the M by itself. And when we divide this whole thing by -1, we basically changing the signs of the E and the K, right? So now we got M by itself equals, and that's going to be what? Negative K plus E, which is actually what? If we switch this around, it's going to be E minus K. That's what because the K is minus, right? The K is negative. So if we put the E first, then we get E minus K. So E minus K is equal to M based on the equation. So every time we subtract the E, that's what I did. E minus K, 2.2. E minus K, 2.2. E minus K, 2.2. K is not applicable there. We don't need. So whatever energy from the light source minus uh, well, really the way you get K is you take the energy minus the light source minus the M. That's the energy you need to move electrons off the plate, 2.2. So that's why these don't work, because 1.81 is not greater than the energy 2.2 needed to get the electrons off the plate. You need more energy. 2.3 is greater than 2.2. You have more energy. You subtract those, and then you get the energy of the electron moving off the plate, because the 2.2 of the 2.3 one was used to get the electron off the plate, and we have an additional 0.11. So hopefully you guys get that. So if we do E minus K by manipulating this equation equals M, and every time you do E minus K on this experiment, you get 2.2. That's why the answer is B, 2.2. Whoa. Takes a long time for some of these. Of course, when you're taking a test, you would not get stuck on this one. I would have moved past this one very fast. Probably would have got it wrong. No, I may have gotten it right. I don't know how much time I would spend on it. But that's the main thing to remember, that when you're taking a test, do not get stuck on questions like this. Okay. Done for that one. I'll start a new one next time. Maybe English or read. All right.